This is 28th lecture, problem session 7. We will take a couple of problems from differential amplifiers and a fairly involved problem from power amplifiers. 3 problems we propose to work out. Before we take up the problem, a small point that we missed in class B power amplifiers, I want to illustrate this. The simple class B power amplifier was like this, RL, and the 2 bases were connected and the input was applied here. Okay. Now this goes to minus VEE and this goes to plus VCC. Now you notice that the current, load current IL is bears the following relationship to IC1 and IC2. IL is the difference between the two, isn't that right? IC1 equal to IL plus IC2, therefore IL equal to IC1 minus IC2. What is the waveform of IC1? If you ignore crossover distortion, or if you have taken care of crossover distortion by using 2 diodes here, then the waveform of IC1 is half rectified sine, and the waveform of IC2 is also half rectified sine but shifted in phase by 180 degrees. Okay, this is the basic form. Now if you expand IC1, this half rectified sine wave or cosine wave, in Fourier series, then because of the symmetry in the waveform you get only cosine terms. There is a DC and only cosine terms, no sine terms, and therefore I can write I sub C1, this half rectified sine wave, as IC1 as some DC A0 plus A1 cosine of omega 0 t, let us say, this is the signal that I have applied, plus its harmonics due to distortion. Okay, because power amplifier are large excursion amplifiers, large excursion of signals, and therefore there will be distortion, and this distortion may be A2 cosine of 2 omega 0 t plus etc. I do not know how many harmonics are there. Fourier series gives infinite number of harmonics. So if we expand this in Fourier series, we get something like this. Similarly, I sub C2, the only difference between IC1 and IC2 is that they are 180 degrees phase shifted. In other words, it becomes A0 plus, this will be minus A1 cosine omega 0 t, then this would be plus A2 cosine 2 omega 0 t, and so on. The next would be minus, and so on. Now if I take the load current IL as the difference between the two, obviously the DC terms cancel, no DC flows through the load, we get twice A1 cosine omega 0 t, and the next term is twice A3 cosine of 3 omega 0 t, okay, and so on. So only the fundamental and its odd harmonics are present. As you know from general experience of Fourier series expansion, that these amplitudes A0, A1, A2 usually for a half rectified sum wave they are in decreasing orders of magnitude, and therefore this second harmonic is the major cause of distortion in I sub C1. Okay, the major harmonic component in I sub C1 is the second harmonic, because the amplitudes are in decreasing order, all right, and the second harmonic gets cancelled out. Therefore class B only retains third and higher harmonics, which means that the THD, total harmonic distortion, would be square root of A3 square, well 4A3 square plus 4A5 square and so on, divided by twice A1. Agreed? This 4, 4 and 2 could be cancelled out. Now this is one of the advantages of class B amplification, that the distortion automatically is less because the strongest harmonic component in either of the two waveforms IC1 and IC2 gets cancelled out. Okay. This is a point in favor of class B amplifier, and of course the point that no DC flows through the load. The DC, the average value of current, is 0. Okay. Now we take up the problems. Okay, we haven't done, I didn't set any problem in the tutorial sheet on FET amplifiers. So, we will take FET differential amplifiers, two examples of FET differential amplifiers. One of them is this. Draw with me a differential amplifier. We didn't discuss the theory in great details either, because the theory was very similar to BJT. So, we shall illustrate this through a couple of examples. We have the Q1, no, I should have drawn like this, Q2, then the two sources, this is the drain, this is the source terminal, the two sources are connected together. So, it is source coupled pair rather than an emitter coupled pair, and then we have an R sigma. This goes to minus VSS, okay, and this current is ISS. ISS naturally is twice of I sub D, okay. ISS is twice of I sub D because of complete symmetry, and then of course you have the signal source here and a signal source here. This is the circuit. Now the problem says that R sub D is given as 50K. Obviously, it is not an integrated, it is not an IC, it is a discrete design. R sub C is R sub D is 50K. IDSS, you require this quantity. This relates current to VGS. IDSS is given as 2 milliampere, and ISS, the biasing is such that ISS is 500 microampere, which means that I sub D is 250 microampere. And in addition, you also require the data on Vp, the pinch off voltage, that is given as minus 3 volt. The questions are to find out the following: A sub D, the differential gain, then R sub sigma if VDD equals to VSS is equal to 10 volt. These two quantities are to be found out, and we also need the CMRR in decibels. These are the problems. These are the given conditions. You require to find out AD, R sigma if VDD and VSS both the supplies are plus minus 10 volts, and the CMRR in decibels. The first thing we do is find out GM. Okay, you know the relationship is ID equal to IDSS 1 minus VGS divided by VP whole squared, and GM is DID dVGS, and we had shown earlier that this can be written as, by differentiating this and simplifying, minus 2 by Vp, and then you could write square root of IDSS. This can be very easily established. We have eliminated VGS. Okay. Small ID and small VGS. Okay. Okay, fine. And we are equating, we are finding this at the Q point. Correct. And this is the story. This is the final result. Now if I substitute the values, you see GM is minus 2 divided by minus 3, I sub D is 250 microamperes, and IDSS is given as 2 milliamperes, 2 times 10 to the minus 3, and so many mhos. If you calculate this out, my result is 471 times 10 to the minus 6 mhos. Why did we find out GM? Because this we require for calculating the differential gain AD. AD, therefore, the differential gain is simply equal to minus GM times RD. Therefore, it is 471 minus times 10 to the minus 6 multiplied by 50 into 10 to the 3. 10 to the 4 minus 2. It comes out as minus 23.6. I don't know how that 0.6 comes. It should have been. Oh, okay. That's what I simplified as 23.6. Okay. Now, in order to calculate R sigma, you first note that from ID, R sigma obviously has to be calculated from a KVL, from application of a KVL. Okay. And that KVL we want to do it through VGS. Okay. VDD, IDRD, VDSQ, and then VGS, then we go to ground. Okay. So, I calculate VGS first. ID is IDSS 1 minus VGS by VP whole square. I know ID, I know IDSS, I know VP, and therefore I can calculate VGS. VGS, my calculation gives it as minus 1.94 volt. It has to be negative. Gate has to be negative with respect to the source. Then I write a KVL. I write a KVL like this. I come from here. I come from here. What is the DC voltage of this point? 0. Because it's a, this source is grounded. For DC there is a resistance. So, VGS plus ISS R sigma minus VSS would be equal to 0. Is that clear? Okay. So, I write this VGS minus, not minus, plus ISS R sigma minus VSS equal to 0, in which we know VGS, we have already calculated minus 1.94 volt, we know VSS, it is 10, we know ISS, which is 500 microampere. Therefore, I can calculate R sigma, and my calculation gives 23.8 K. Finally, I require the CMRR, and if I know GM and R sigma, CMRR is clear. It is 1 plus twice GM R sigma. It was 1 plus twice GM R EE in the earlier case. It is R sigma, and if you substitute the values, this comes out as 22.44. I am skipping this numerical calculation. I have already done that. So, I don't guarantee that it is correct. So, I urge you to verify this. Now, the point is you have to find CMRR in dB. So, you write not equal to, equivalent to, okay, 3 parallel signs. 22.44 is the ratio of AD to AC. If you want to calculate this in dB, this is 20 log 10 of 22.44, which is equal to, now you can write an equal to sign. Be careful about this, okay. You cannot write 22.44 equal to 20 log 10 22.4. It is equivalent to, okay. So, 3 signs, and this comes out as 27.4 decibels, my calculation. I made some mistake, numerical mistake somewhere. So, you please do check this. The second problem that we want to take up is a design problem. The problem is to design a source coupled JFET N channel JFET. Design a source coupled N channel JFET differential amplifier that meets the following specifications. To meet the following specifications, one is that the differential gain should be minus 10, the VDSQ at the Q point, it should be equal to 5 volt. Under this condition, compute the CMRR. What is the CMRR? For your design, what is the value of CMRR in decibel, CMRR in dB, that is what is wanted, and the data given about the N channel JFET is that IDSS, this must be given, is 1 milliampere. It may be given directly or indirectly, okay. It may be given such that when VGS equal to this much, the drain current is this much. This indirectly gives you IDSS. So you will have to find this out. IDSS 1 milliampere, VP is minus 3 volt. It is also given that the load is restricted to be 20 K, and it is given that small RD, if small RD is not negligible, is not infinite, then you have to parallel it with whom? Capital RD, capital R subcapital D. Small RD is given as negligibly large. Okay, it's so large that its effect can be neglected. Okay. Now the first thing we do is we start from AD, because we know RD, therefore we can find out GM. AD is minus 10, this is given, and this should be equal to minus GM times RD is 20 K, and therefore we find out GM. GM is 0.5 millimole. GM is also equal to minus 2 divided by VP square root of ID IDSS, okay, and which we know we know VP, we know IDSS, therefore I can calculate ID, okay, the drain current. Therefore ID, which is equal to GM square VP squared divided by 4 IDSS, this calculates out to 0.56 milliampere. And if I know ID, then I can also calculate VGS, which I require. VGS is given by VP multiplied by, I beg your pardon, that is not correct. From the relation ID equal to IDSS 1 minus VGS by VP whole squared, I get VGS is equal to VP, then 1 minus square root of ID by IDSS, okay, and this calculates out as minus 0.75 volt. All right. So the design means what? You have to fix the supplies now. VDD, VSS, and what else? In the simple differential amplifier, R sigma. Now, for VDD, you notice that VDD is equal to IDRD plus VDSQ, which is given, the operating point is given. Then when you go to S, you can then go to the ground via VSG, which is minus VGS. Agree? Is this equation clear? We come from VDD, IDRD, VDSQ, then from source to ground via gate VSG, which is minus VGS. So let's substitute the values, then we get this as 0.56 milliampere multiplied by RD is 20 K, VDSQ is given as 5, minus VGS would be plus 0.75, and this comes at 16.95 volt. Okay, an odd value, but it can be adjusted. You can make slight adjustment in RD to make it 17 volts or reduce it to 15 and so on. Now as far as VSS is concerned, for VSS we can write the following equation: VGS plus ISS, we are coming from the ground, VGS plus ISS multiplied by R sigma, then minus VSS equal to 0. Now we know VGS, which is minus 0.75, we know ISS, how much is that? 1.02, twice 0.56, okay, multiplied, this is milliampere. So if I write R sigma, this will be in K, alright, minus VSS equal to 0. What is 7.1? Oh, this is 1.12, yes, 0.56 multiplied by 2 is 1.12, I agree, I could not but agree, okay. Now the point now is, from one equation, obviously we have no other knowledge. From one equation we cannot determine two quantities, but it's a problem of design. Therefore you should be happy, you can choose one according to your convenience. Now if you have chosen VDD to be equal to 16.95, there is no reason why VSS cannot be minus 16.9. So you choose VSS as 16.95 volts, chosen. Then you can find out R sigma, and this R sigma comes at 15.8 K. Is the point clear? There is one equation, two unknowns, you choose one, and the guideline is you choose VSS equal to VDD. There is no hard and fast rule. You could choose VSS. Could you choose VSS equal to 0? 0? Why not? No, but the drop in R sigma, how can you avoid that? VGS should be negative. So VG is 0, VS should be positive. Okay? Now R sigma, what I am saying is, could this be taken to 0? This is ISS flowing through this. So this potential obviously will be positive.
VSS plus ISS R sigma should be greater, should be less than 0.
That is right. That condition VGS should be, VDS should be greater than VGS minus VP. That puts a constraint. In some cases you may be able to put VSS equal to 0. But as I said, there is no point in choosing a VSS equal to 0. You have a power supply, and all power supplies usually, IC power supplies, are plus minus and equal voltages. There is no reason why you cannot choose this. So finally we calculate the CMRR as equal to 1 plus twice GM R sigma. Everything is known, and therefore this ratio comes at 16.8, and my calculation shows that it is 24.5 decibel. Done. What else was needed in this? CMRR, and that's all. Okay. The last problem of the day. Please pay attention to this, because through this problem I also want to illustrate a practical output stage of an operational amplifier, and this op amp is mu A 725, not 741, 725, the actual circuit I am going to draw, and then set out what the problem, what we are required to calculate. The actual circuit is this. You will see that the numbers of the transistors are very large numbers. I mean, these are parts of the total circuit. So I am drawing only the output stage. Output stage is required to drive some current through a load, and therefore it is a power amplifier stage. It is a class AB stage, so that there is no distortion. Okay, the output stage Q21, and then this goes to plus VCC. I would like to start from another page, because it is a fairly large circuit and I cannot lose space. VCC, this goes to Q21, which is an NPN transistor. Then we have a resistance R16. This is a variation in the class B stage. Okay, R16, which is 25 ohms. We have another resistance also R16 which is also 25 ohms. It has to be symmetrical. In all the circuits that we drew so far, the emitter was connected to the collector of the next transistor, but here it is connected through two resistors, and then of course we have the PNP transistor, and this is Q26 and Q26 goes to minus VEE. The collector goes to minus VEE. The load is connected from here, from the middle point. Obviously it has to, from the symmetry. I will explain the purpose of the R16 a little later, and then you have the RL here, and of course the voltage output is across the RL V0T. Now from the collector you require the drive. To avoid crossover distortion, you require two diodes which have exactly 0.7 drops. Okay, those diodes are obtained in a peculiar manner. This base, the base of Q21 goes to a diode connected transistor Q18. These numbers are there because there are other transistors which you are not drawing. Okay, this is a diode connected transistor, but not from here, it is from this base. Okay, and in order to drive a current through this, we require a resistor, we require a resistance from here which is R15. Okay, then we require another such diode connected transistor, but for reasons of the overall mu S725 design, it is connected like this. It is not connected as a diode, it is connected like this. This is VIT. The input from the previous stage. The previous stage could be a differential amplifier. Okay, and instead of getting this connected as a diode, this is connected like this. Does this make a difference? As far as the balancing is concerned, this base to emitter shall be 0.7 and this base to emitter shall also be 0.7. All that we needed was that this junction should be the same potential as this junction, and from symmetry there is no reason why these two voltages should not be equal. Q18 and this is Q19 are identical transistors, and therefore they should, the voltages at the base VBE should be identical. Okay. Now why these are 16s? What is happening is that there are two more transistors. I will shortly explain why this is so. There are two more transistors, Q23, and the emitter is connected here, the base is connected here. Is the connection clear? The base is connected here, that means the base to emitter, across the base to emitter there is a resistance R16, and a very similar thing repeating here, that is you have a PNP transistor like this, this comes here and the base is connected here, absolutely symmetrical. This is Q24, is there a 24 here? No, this is Q24. Okay, and like R15 there is an R15 here. VCC and VE are usually identical. Why is this R15? To be able to drive this transistor, the PNP transistor. Okay, this is the actual circuit, what goes on inside the 725, actual circuit of the output stage of a mu A725 amplifier. Okay, I have already explained the purpose of Q18 and Q19. These are to avoid the crossover distortion. Now why Q23 and Q24? Let me first explain qualitatively, then I shall discuss what the problem asks for. Qualitatively, you see, suppose Suppose R16 was not there, R16 is 0, this transistor is not there, R15 is there to be able to drive the base of Q21 and Q18 and Q19. Okay. Suppose R16, Q23 are not there. Alright. Then if RL is accidentally short circuited, okay, if RL is very low, then what is the drop across Q21 collector to emitter? It is VCC plus 15 whatever voltage it is. Okay. Now therefore Q21 will draw a large current and it might go, we don't know what the VCC supply is, it might go into the breakdown region, or it might get so saturated that it is difficult for it to come out of saturation. Saturation means charge accumulation, and the charge requires a long time to come out of saturation. Okay. So this resistance and Q23, the two together, the function for R16 and Q24 exactly the same during the negative half cycle of the input voltage. Okay. So it suffices to consider the positive half cycle. During the positive half cycle, Q21 is supposed to conduct, and if R16 is 0 and RL becomes accidentally short circuited, the transistor Q21 will have to put up with the full drop of VCC from its collector to emitter. It may be too much for the transistor. On the other hand, if Q23 and R16 are there, then when the drop IC1 is small, when the collector current of Q21, IC21, when it is small, the drop across the base to emitter of Q23 will be less than VBE23 on, which is about 0.7, and therefore Q23 does not come into the picture and the total current goes to the load RL. But as soon as IC21 is large enough to make the transistor Q23 on the verge of conduction, okay, then what happens is the input current does not totally go to Q21, right. When this transistor starts conducting Q23, the input current has to have two parts. One goes through IC23 and the other is IB21. So IB21 is not equal to the input current, it is only a part of the input current, and therefore when IC21 increases, IB21 decreases, and if IB21 decreases, IC21 also decreases. Alright, which means that this voltage is limited to 0.7 approximately, taking Q23 into the active region, and therefore IC21, well, if you write the current equation at this junction, IC21, this is the same, IC21 minus IB23 should be equal to the load current. Okay, no, there is another current here, IE23. So if I write the equation IC21 minus IB23 then plus IE23 should be equal to IL. Agree? Minus when Q23 conducts, Q24 doesn't. You see, this half does not carry any current when the other half is carrying current, right? This is the class B stage. The Q21 conducts, Q26 is off. Q26 conducts in the negative half cycles, Q21 is off. So it suffices to consider only the upper half of the circuit. Okay, so now these IB23 and IE23 obviously are much smaller compared to IC21. The beta is usually very large, so IB23 can be ignored IE23, which is a part of IB21. Previously we had IB21, part of it is diverted as IC23. Therefore, these two currents are very small, and since IC21 is constrained to have a maximum value of VBE23 divided by
25.
R16, IL is also constrained. Agreed? In other words, this Q23 and R16 have been used for the purpose of short circuit protection. Okay? Short circuit protection. That is, if accidentally RL becomes short, a large current cannot flow through this transistor Q21. Agreed? A large current cannot flow. So, it is a short circuit protection. Now, in this problem, what is asked for is the following. Please follow this carefully. Have you been able to draw the circuit? Totally? Okay. What is being asked for is the following. Let VEE equal to VCC equal to 15 volt and RL is given as 2K. First, you neglect the effects of the 25 ohm protection resistor for normal operation. That is, the 25 ohm protection resistor is not there. First, ignore R16. The question that is asked is, what is the maximum average power this circuit can deliver, that can be delivered to the load, What is the maximum average power that can be delivered to the load by this circuit? Okay, this answer is absolutely simple. What is the maximum swing that is permitted across the load? Maximum possible swing. Pardon me? What is the maximum load that can be permitted? Ignore the effect of R16. R16 is VCC minus VC sat. Okay, and therefore the answer to this question is very simple. If VC sat is ignored, compared to 15, 0.2 can be ignored, it will simply become 15 squared Vm squared divided by 2 RL, that is 2 times, why 2? Because it is the root mean squared value. Okay, Vm divided by root 2 is the root mean squared value, 2 times, and RL is how much? 2K, and this comes out as 56.25 milliwatt. This is the answer, simple answer. This has nothing to do with the complication of the circuit and things like that. All right? Okay. If you are fussy, instead of 15, you take 14.8. Okay? If you do not want to ignore that VC is set, you take 14.8. Part B. At this power level, that is 56.25 milliwatt, at this power level, what is the power required to be delivered by the power supply? How much power is required to be delivered by the power supply? That is, how much is PDC? If you recall, we found out this as twice VCC multiplied by VO max divided by pi RL. VO max by pi was the DC, average DC current, VO max by pi RL, and we multiply by twice VCC, that is VCC minus VEE. Okay. Now, we know everything, we know VCC is 15 volt, we know RL, we know VO max. Again, we take either 15 or 14.8. I have taken 15 and it comes out as 71.6 milliwatt. Can you see what the efficiency is? Eta C is therefore 56.25 divided by, yes, 71.6 multiplied by 100. Is this a correct figure? How much is this approximately? Approximately 75%. All right, that's not too bad, because your maximum is 78.6%. Your maximum is 78.6. This, I guess, is more than 75. It's more than, no, it cannot exceed 78.6. All right. Okay. The last question. Pardon me?
78.56.
That's the actual value. That's what I expected. I didn't expect a large drop like 75. Why didn't I expect it? Because we have calculated. Pardon me? 78.57. Okay. Approximately 78.6. Now why I was fussy about this figure? Why didn't I get satisfied with 75? Because we have calculated under the maximum possible swing. We even ignored VC set, and that there is no reason why it should not come to 78.6%. It should be coming to pi by 4. All right, 78.57 is okay. It must be because of my rounding in the powers, Otherwise, it should have been exactly 78 point. That's pi by 4. The last part of the question. What was the last part of the question? Or I have not given you the last part of the question. No, I have not spelled out yet the last part of the question. Last part of the question is, what is the smallest RL? Smallest RL that can be used before the protection circuitry starts to operate. Smallest RL that can be used before the protection circuitry starts to operate. Now, how do I attack this problem? To attack this problem, we see that I sub C1, I sub C21, that upper transistor, that is limited, that is the maximum possible value that IC1 can have, all right, to make 23, Q23 just on, is given by VB on, that is 0.7 divided by, that is 25 ohms. Okay, that is equal to 28 milliampere. All right, take 0.5. If VB on is 0.5, we have taken this figure as 0.5. You can take 0.5. If this is 0.5, obviously this will be 25 milliampere. Okay. Now, if IC1 is limited to 25 milliampere, it cannot increase beyond that. Obviously, this must be equal to the maximum value of the load current, ILM. Agree? So ILM is equal to 25 milliampere. Oh, okay. Okay, I stand corrected. So the maximum load current must also be 20 milliampere. Load current cannot exceed the maximum I sub C 21. And if this is the maximum load current, then the minimum load RL mean at which this will occur is given by VCC. Why VCC? Because this is the maximum swing across the load. So VCC divided by IL max, which is equal to 15 divided by 20 milliamps. That is equal to how much is that? 750 ohms. Is that right? Milliamps, 15,000 divided by 20, 750. Now we should account for the drop in R16. Okay, let's go back. Good question. R16 is 25 ohms. 25 ohms. So this swing cannot go to 15 volt. It must be 15 minus ILM multiplied by 25. Is that clear? So this would be slightly less, but the end justifies the means. We found out this load, minimum load, to be 750 ohms. Obviously, when RL goes below 750, suppose RL becomes comparable with R16, then obviously the efficiency would be decreased. Efficiency would be hard. But on the other hand, if RL minimum is much larger as compared to 25, 750 is 30 times, and therefore this drop is negligible and the efficiency level is maintained. We are justified in ignoring the drop in 25 ohms because the ultimate value that we get by ignoring this is 750. But suppose RL goes to 25 ohms or goes towards short circuit, then obviously R16 will consume the major power, alright, and the efficiency will go down, go zooming down. Okay, that is a good point to stop. I have given 3 interesting problems in the tutorial sheet which you should try to solve.